Welcome to the course Part 4, Statistics for Data Science and Business Analysis. Part 4, What You'll Learn. Lecture 41, Introduction to Regression Analysis. Lecture 42, Correlation and Causation. Lecture 43, The Linear Regression Model Made Easy. Lecture 44, What is the difference between correlation and regression? Lecture 45, A Geometrical Representation of the Linear Regression Model. Lecture 46, A Practical Example, Reinforced Learning. Lecture 47, Decomposing the Linear Regression Model, Understanding its Nuts and Bolts. Lecture 48, What is R-squared and how does it help us? Lecture 49, The Ordinary Least Squares Setting and its Practical Applications. Lecture 50, Studying Regression Tables. Lecture 51, The Multivariate Linear Regression Model. Lecture 52, Adjusted R-squared. Lecture 53, What does the F-Statistic show us and why we need to understand it? Lecture 54, OLS Assumptions. Lecture 55, A1_linearity. Lecture 56, A2_ No Endogeneity. Lecture 57, A3_ Normality and Homoscedasticity. Lecture 58, A4_ No Autocorrelation. Lecture 59, A5_ No Multicollinearity. Lecture 60, Dummy Variables. Lecture 61, Practical Example _ Regression Analysis. Lecture 41, Introduction to Regression Analysis.
With some solid statistical knowledge behind us, we are ready to jump into regression analysis, which is arguably the most common method of prediction. It is used whenever we have a causal relationship between variables. For example, among other factors, the money you spend depends on the money you make. In the same way, the time you devote to this course depends on your motivation to learn statistics. We will use our typical systematic approach, starting from the simple linear regression model and reaching the multivariate regression model. Along the way, we will learn how to build a regression, how to interpret it, and how to compare different models. We will develop a deep understanding of the fundamentals, as what we'll learn in this section will be closely related to the knowledge we've acquired so far. After this section, you will be prepared to dive into more advanced statistical analysis or even machine learning, if that's where you want to go. Brace yourselves. Regression analysis starts here.
Lecture 42, Correlation and Causation.
Hi again. After we have introduced the topic, this lesson will be a lot more quantitative. In the first section of the course, we talked about correlation, remember? Let's do a quick recap. First, how do we identify a correlation between two variables? Well, one way is to plot them on a scatter plot or a line chart and try to find a pattern. However, as we are getting more acquainted with statistics, we would prefer using the correlation coefficient. Here are the formulas we saw earlier. Alright, let's explore a few examples of correlated variables, shall we? Here, we have three datasets. The first one represents the number of movies Vin Diesel makes per year. The second, the US GDP growth rate. And the third, the UK GDP growth rate. You can already sense this will be an action-packed video. Let's find the correlation coefficients of these datasets. I would like to remind you that the correlation coefficients are values from -1 to +1, where 0 shows no linear relationship, 1 a very strong positive correlation, and -1 a very strong negative correlation. The correlation of Vin Diesel movies and the US GDP growth rate is 0.43. What's the meaning of this value? Well, a far-fetched explanation would be that when times are good and GDP rises, Vin Diesel makes more movies and vice versa. Okay, if we calculate the correlation of Vin Diesel movies and the UK GDP growth rate, we get 0.46. The number of movies he makes has a stronger correlation with the UK GDP growth, although Vin works in the USA and supposedly has nothing to do with the UK. Suddenly, our previous explanation does not sound convincing. Finally, the correlation of US GDP growth rate and UK GDP growth rate is 0. Wait, what's going on? This doesn't make any sense. We have to make a few considerations though. First, does it sound reasonable that gigantic countries like the USA and the UK will have anything to do with Vin Diesel starring in a film? Of course not. The result we got is pure coincidence. I assure you that many things in the world are correlated, some even more absurd than our example. But correlation does not imply causation. It's easy to find correlations, but much harder to find causal relationships. To exhaust this example, we should also comment on the lack of correlation between the US and the UK GDP growth rate. Well, our sample is drawn from the period 2010 to 2015, which is shortly after the US subprime mortgage crisis and during the European sovereign debt crisis. The US and UK were coping with their respective situations in different ways, and the results were mixed. As you can see, the low correlation does not mean one country was doing better than the other. It shows their stronger and weaker times were not coinciding in our sample period. However, history tells us that American and European historical growth rates have had a causal relationship because of trade, war, and movement of capital and labor. Alright, after seeing these three cases, what's the bottom line? Correlation does not imply causation. This whole lesson was to illustrate that some variables are strangely correlated, while others are unexpectedly uncorrelated. In regression analysis, you will often start with a correlation test to see what's going on with your data. But be wary, as the results could be misleading. In the following lessons, we will get familiar with regressions. We will take extra time to distinguish between correlation analysis and regression analysis. Alright, to conclude, let's say it again. What's the key takeaway from this lesson? That's right, correlation does not imply causation. Thanks for watching.
Lecture 43, The Linear Regression Model Made Easy.
Hi, it is time for the actual introduction of regressions. Let's start with some dry theory. A linear regression is a linear approximation of a causal relationship between two or more variables. Regressions models are highly valuable as they are one of the most common ways to make inferences and predictions. The process goes like this. You get sample data, come up with a model that explains the data, and then make predictions for the whole population based on the model you have developed. There is a dependent variable labeled y being predicted and an independent variable labeled x1, x2, and so forth. These are the predictors. Y is a function of the x variables, and the regression model is a linear approximation of this function. The easiest regression model is the simple linear regression. Y is equal to beta 0 plus beta 1 times x plus epsilon. Let's see what these values mean. Y is the variable we are trying to predict and is called the dependent variable. X is the independent variable. When using regression analysis, we want to predict the value of y, provided we have the value of x. But to have a regression, y must depend on x in some causal way. Whenever there is a change in x, such change must translate into a change in y. Think about the following equation. The income a person receives depends on the number of years of education that person has received. The dependent variable is income, while the independent variable is the years of education. There is a causal relationship between the two. The more education you get, the higher income you are likely to receive. This relationship is so trivial that it is probably the reason you are watching this course right now. You want to get a higher income, so you are increasing your education. Now, let's pause for a second and think about the reverse relationship. What if education depends on income? This would mean the higher your income, the more years you spend educating yourself. Putting high tuition fees aside, wealthier individuals don't spend more years in school, and high school and college take the same number of years, no matter your tax bracket. Therefore, a causal relationship like this one is faulty, if not plain wrong. Hence, it is unfit for regression analysis. Let's go back to the original example. Income is a function of education. The more years you study, the higher income you will receive. This sounds about right. Alright, what we haven't mentioned so far is that in our model, there are coefficients. Beta 1 is the coefficient that stands before the independent variable. It quantifies the effect of education on income. If beta 1 is 50, then for each additional year of education, your income would grow by $50. In the USA, the number is much bigger, somewhere around $3,000 to $5,000. So, for each additional year you spend on education, your yearly income is expected to rise by $3,000 to $5,000. And that's not considering higher education or tailored courses, like this one. The other two components are the constant beta 0 and the error, epsilon. In this example, you can think of the constant beta 0 as the minimum wage. No matter your education, if you have a job, you will get the minimum wage. This is a guaranteed amount. So, if you never went to school and plug in an education value of 0 years in the formula, the regression will predict that your income will be the minimum wage. Makes sense, right? The last term is epsilon. This represents the error of estimation. The error is the actual difference between the observed income and the income the regression predicted. On average, across all observations, the error is 0. If you earn more than what the regression has predicted, then someone earns less than what the regression has predicted. Everything evens out. Alright, the original formula was written with Greek letters. What does this tell us? It was the population formula. But we know statistics is all about sample data. In practice, we use the linear regression equation. It is simply y hat equals b0 plus b1 times x. You heard it right. The y here is referred to as y hat. Whenever we have a hat symbol, it is an estimated or a predicted value. b0 is the estimate of the regression constant beta 0, while b1 is the estimate of beta 1, and x is the sample data for the independent variable. This will do for now. We will discuss this equation in more detail in the next lessons.
Lecture 44. What is the difference between correlation and regression?
Before we go any further, what did we say about correlation? Correlation does not imply causation. Let's spend one more minute on that. First, correlation measures the degree of relationship between two variables. Regression analysis is about how one variable affects another or what changes it causes to the other. Second, correlation doesn't capture causality but the degree of interrelation between the two variables. As with Vin Diesel movies, variables were moving together but were not causing each other. Regression is based on causality. It shows no degree of connection but cause and effect. Third, a property of correlation is that the correlation between x and y is the same as between y and x. This you can easily see from the formula, which is symmetrical. Regressions of y on x and x on y yield different results. Think about our example with income and education. Predicting income based on education makes sense, but the opposite does not. Finally, the two methods have very different graphical representation. Linear regression analysis is known for the best fitting line that goes through the data points and minimizes the distance between them, while correlation is a single point. Alright, hopefully this short video clears some doubts you had. Stay tuned.
Lecture 45. A geometrical representation of the linear regression model.
Let's check out the simple linear regression equation once again. Here it is. You have probably heard of the regression line, right? When we plot the data points on an xy plane, the regression line is the best fitting line through the data points. Okay, here's a plot with some data points. We plot the line based on the regression equation. The gray points that are scattered are the observed values. b0, as we said earlier, is a constant and is the intercept of the regression line with the y-axis. b1 is the slope of the regression line. It shows how much y changes for each unit change of x. The distance between the observed values and the regression line is the estimator of the error term epsilon. Its point estimate is called residual. Now, if you draw a perpendicular from an observed point to the regression line, the intercept between that perpendicular and the regression line is a point with a y value equal to y hat. As we said earlier, given an x, y hat is the value predicted by the regression line. Okay, our next lesson will be an example of what we have seen so far.
Lecture 46. A practical example, reinforced learning.
It's time for an example, isn't it? What we have here is a database with SAT grades and college GPA. Alright, so we have a sample of 100 students who studied in a given college. Their total SAT scores include critical reading, mathematics, and writing, and the GPA is the grade point average they had at graduation. So, what would we do if we had to use our knowledge from previous sections? The most logical thing would be to see what is the correlation between the two variables, SAT grades and GPA. The sample correlation is 0.64. We could then further test if this correlation is significant by using hypothesis testing, and we would confirm that the two variables are correlated. Then what? These tests did not give us any information about any under or overachievers. We have no predictive ability except for saying the two scores move in the same direction. Well, this is a problem that regression analysis is designed to address. So let's get onto it. You can see two scatter plots. In the first one, on the x-axis, we have a student's SAT score, and on the y-axis, his GPA. In the second one, the situation is reversed. On the x-axis, we have the GPA, and on the y-axis, the SAT score. We have also included the regression lines. Alright, we have two regressions, right? Should we use both to make predictions? Well, this is the hardest part of regression analysis. In this case, one provides a valuable insight, and the other is plain wrong and utterly deceivable. The two variables are definitely correlated. We already tested that. But what's the causal relationship, if there is one? Let's think about the problem. You attend the SAT and get a score. With this score, you apply to college. The next 4 years, you attend college and graduate receiving many grades, forming your GPA. So, that's your timeline. What does this mean? Well, the SAT test is taken before you sit any exams in college and have a GPA, actually 3 to 5 years before that. Is there any logic in predicting SAT scores using your college graduation GPA? No, there isn't. This is like predicting how much you spent yesterday based on how much money you found on the street today. No logic whatsoever. Therefore, the second regression is meaningless. What's the takeaway? Whenever you find data that looks regressible, you should not dive straight into regression analysis. Caution and logic should be applied beforehand. Alright, so I am saying we should predict college GPA using SAT scores. But don't believe me just yet. Use your logic instead. Ask yourself, what's rationale? Well, the SAT is considered one of the best estimators of intellectual capacity and capability. On average, if you did well on your SAT, you will do well in college and at the workplace. Almost all colleges across the USA are using the SAT as a proxy for admission. The SAT stood the test of time and established itself as the leading exam for college admission. It is safe to say our regression makes sense. Okay, after we've cleared things up, we know which of the two graphs we should focus on. You can see the best fitting line between the points, also known as the regression line. Our dependent variable, y, is college GPA. The independent variable, x, is the SAT score a student received. The equation that determines the regression line is y hat equals 0.48 plus 0.0015 times x. Okay, how can we use this equation? Say you got 1,700 on your SAT. You plug it in and get a GPA of 3.03. Interpreting this result is, if you attended this specific college and were admitted with an SAT score of 1,700, the model predicts you will graduate with a GPA of 3.03. What if you got 2,000 on your SAT? Your GPA would then be near 3.48. You get the gist of how powerful regression analysis can be. However, there are pitfalls. What if you got 2,400 on the SAT? The predicted GPA is 4.08. More than the maximum. Here, we touch upon the limitations of regression analysis. As the maximum SAT score we had in our sample was 2,050, it is not correct to make predictions for data points that are outside the regressed dataset. A possible rationale may be, People that got over 2,050 on the SAT went to better universities, where it is much harder to get such a high GPA. All the data was coming from the same college. Therefore, the profile of a typical student there is very specific. It may be an engineering college or an arts college. These factors and many more affect the result, so you should know your data. But don't worry, we will see enough examples so you will become confident with identifying and interpreting regressions. Keep up the good work, and thanks for watching.
Lecture 47, Decomposing the Linear Regression Model, Understanding its Nuts and Bolts.
We already saw the regression equation and an example of a regression model. In this lesson, we will explore the determinants of a good regression. This video is based on the ANOVA framework you may have heard before. There are three terms we must define: the sum of square totals, the sum of squares regression, and the sum of squares error. The sum of squares total, denoted SST, is the squared differences between the observed dependent variable and its mean. You can think of this as the dispersion of the observed variables around the mean, much like the variance we saw in descriptive statistics. It is a measure of the total variability of the dataset. The second term is the sum of squares regression, or SSR. It is the sum of differences between the predicted value and the mean of the dependent variable. Think of it as a measure that describes how well your line fits the data. If this value of SSR is equal to the sum of squares total, it means your regression model captures all observed variability and is perfect. The last term is the sum of squares error, or SSE. As we've said in one of the previous videos, the error is the difference between the observed value and the predicted value. We usually want to minimize the error. The smaller the error, the better the estimation power of the regression. So, what is the connection among these three? Mathematically, SST is equal to SSR plus SSE. The rationale is the following. The total variability of the dataset is equal to the variability explained by the regression line plus the unexplained variability, known as error. Given a constant total variability, a lower error will cause a better regression. Conversely, a higher error will cause a less powerful regression. Makes sense, right? Alright, based on this knowledge, in our next lesson, we will learn how to compare different regression models. Thanks for watching.
Lecture 48, What is R-squared and how does it help us?
Hi again. So far, we decomposed the total variability of the observed data into explained and unexplained. We've also noted the smaller the regression error, the better the regression. But this is statistics, so there must be at least one widely used measure that describes how powerful a regression is, right? Well, fortunately or unfortunately, depending on your attitude, there is. Let me introduce you to the R-squared. The R-squared is an intuitive and practical tool when in the right hands. It is equal to SSR divided by SST. As you should recall, SSR is the variability explained by the regression, while SST is the total variability of the dataset. So, what does it mean? It's a relative measure that takes values ranging from 0 to 1. An R-squared of 0 means your regression line explains none of the variability of the data. An R-squared of 1 would mean your model explains the entire variability of the data. Unfortunately, regressions explaining the entire variability are rare. What you will usually observe is values ranging from 0.2 to 0.9. The immediate question any student is compelled to ask is, what is a good R-squared? When do I know for sure my regression is good enough? I regret to inform you there is no definite answer to that. In the field of physics and chemistry, scientists are usually looking for regressions with R-squared between 0.7 and 0.9. However, in social sciences, such as economics, finance, and psychology, an R-squared of 0.2 or 20% of the variability explained by the model could be fantastic. It depends on the complexity of the topic and how many variables are believed to be in play. Think about income once more. It may depend on your household income, including your parents and spouse, your education, years of experience, country you are living in, languages you speak, and this may still account for less than 50% of the variability of income. Your salary is a very complex issue, but you probably know that. Let's check an example we saw before: SAT score and college GPA. We said that the SAT score is one of the better determinants of intellectual capacity and capability. The truth is that our regression had an R-squared of 0.406, or in other words, SAT scores explain 41% of the variability of the college grades for our sample. An R-squared of 41% is neither good nor bad, but since it is far away from 90%, we may conclude we are missing some important information. Other determinants must be considered. Variables such as gender, income, and marital status could help us understand the full picture a little better. Okay, should we move on? Wait, what did I say in this section? Don't jump into regressing. Critical thinking is crucial. Before agreeing that a factor is significant, you should try to understand why. So let's quickly justify that claim. First, women are more likely to outperform men in high school, but then in higher education, more men enter academia. There are many biases in place here. Without telling you if female or male candidates are better, scientific research shows that a gender gap exists in education. Gender is an important input for any regression on the topic. The second factor we pointed out is income. If your household income is low, you are more likely to get a part-time job. Thus, you'll have less time for studying and probably get lower grades. If you've ever been to college, you will surely remember a friend who underperformed because of this reason. Third, if you get married and have a child, you'll definitely have a lower attendance. Contrary to what most students think when in college, attendance is a significant factor for your GPA. You may think your time is better spent when skipping a lecture, but your GPA begs to differ. Alright, after these clarifications, let's find the bottom line. The R-squared measures the goodness of fit of your model. The more factors you include in your regression, the higher the R-squared. So, should we include gender and income in our regression? If this is in line with our research and their inclusion results in a better model, we should do that. However, we'll talk about regressions with more variables later in the course. In this lesson, we built a solid understanding of how R-squared functions. Excellent! Next, we will learn how to find a regression's regression line.
Lecture 49, the ordinary least squares setting and its practical applications.
Okay, great. So, we've arrived at the point where we will learn how to find the regression line. The most common method to do that is called the OLS, or the ordinary least squares method. Least squares stands for the minimum squares error, or SSE. You may recall that a lower error results in a better explanatory power of the regression model. So, this method aims to find the line, which minimizes the sum of squared errors. Alright, let's clarify things with this graph. We can find many lines that fit the data. The OLS determines the one with the smallest error. Graphically, it is the one closest to all points, simultaneously. The expression used to do this is this one. But how is this formula applied? Well, this is a minimization problem that uses calculus and linear algebra to determine the slope and intercept of the line. After you crunch the numbers, you'll find the intercept is b0 and the slope is b1. Knowing the coefficients, here you have it, your regression equation. We can try minimizing the squared sum of errors on paper, but with datasets comprising thousands of values, this is almost impossible. Nowadays, regression analysis is performed through software. Beginner statisticians prefer Excel, SPSS, SAS, and Stata for calculations. Data analysts and data scientists, however, favor programming languages like R and Python as they offer limitless capabilities and unmatched speed. Finally, we must note that there are other methods for determining the regression line. They are preferred in different contexts. Such examples are the Bayesian regression, the kernel regression, and the Gaussian process regression. However, the least squares method is simple, yet powerful enough for many, if not most problems. we will stick with it. Thanks for watching.
Lecture 50, Studying Regression Tables.
When you perform regression analysis using software, you'll find something different than a scatter plot with a regression line. The graph is a visual representation, and what we really want is to have the equation of the model and a measure of its significance and explanatory power. This is the reason the software provides a couple of tables instead of a graph. In this lesson, we will learn how to read and understand these tables. Typically, we will have three main tables: a model summary, an ANOVA table, and a table with coefficients. Here's what we have in Excel. These tables contain all kinds of information, so let me quickly clear it up. We want to see only information that is important and relevant. Alright, first we have the model summary. It will contain the R-squared, the sample size, and the standard error of the estimate. We already know what the R-squared is. The standard error of the estimate, similarly to the standard errors we have seen so far, is a correction of the standard deviation that takes into account the sample size. The formula is square root of SSE divided by n-2. We will not dig deeper into this topic, but as we had with inferential statistics, the bigger the sample size, the lower the standard error, and the better the model. The second table is ANOVA. ANOVA is an abbreviation of Analysis of Variance and is a collection of statistical models used for comparing means. In the context of regressions, the ANOVA table summarizes the variance we've talked about so far: SST, SSR, and SSE. In the ANOVA table, you will also find the F-Statistic, which we will discuss in a separate lesson. The third table is the coefficients table. If you are new to regression analysis, you wouldn't know, but this is the heart of the regression, so get excited. The first row describes the intercept, while the second row, the independent variable. Okay, now let's go column by column. The first one is about the coefficients. We can see the coefficient of the intercept is 0.4803, which means B0 is 0.4803. Looking below, we notice the other coefficient is 0.0015. This is our B1. These are the only two numbers we need to define the regression equation. Y hat equals 0.4803 plus 0.0015 times x. That is also the correct way to get the regression equation. Next, we have the standard errors of each estimate, which we will need in a second. The two values are a t-statistic and its p-value. If you have paid close attention to the course, you will know there is a hypothesis involved here. The null hypothesis of this test is beta equals 0. In other words, is the coefficient equal to 0? If a coefficient is 0 for the intercept, B0 that is, then the line crosses the y-axis at the origin. If beta 1 is 0, then 0 times x will always be null for any x, so this variable will not be considered for the model. Let's paraphrase the null hypothesis. Essentially, it means, is this variable useful? Does it help us explain the variability we have in this case? The answer is contained in the p-value column. As we've discussed earlier in this course, we are longing for those three zeros. But it is up to the researcher to choose the significance level. In our example, the SAT score is significant in determining college GPA. What you may notice is that the intercept p-value is not 0. Let's think about this. Does it matter that much? Even if the p-value is large, the intercept is insignificant, so the test is about, do we have enough statistical evidence that the intercept differs from 0? Usually, this is not essential, as it is the x's we are interested in. Alright, starting from our next lesson, we will get into more serious regression analysis by exploring multivariate regressions.
Lecture 51, the Multivariate Linear Regression Model.
Okay, excellent. So far, we learned about the simple linear regression. We predicted the dependent variable y with a single regressor, x. It is time to level up now. We said that, in real life, a person's income does not depend solely on education, but also their experience, the time they have spent with their current employer, and so on. House prices do not depend on solely their size, but also on location and year of construction. College GPA cannot be predicted solely by a student's SAT score, but also by their high school GPA, income, gender, and so on. If we want to make good models, we need multivariate regressions. Multivariate regressions address the higher complexity of problems. The more variables you have, the more factors you are considering in a model. In the real world, things depend on 2, 3, or even 10 or 20 factors. Alright, so this is the population multivariate regression model. It is similar to a simple regression. The main difference is there are a bunch of independent variables, not just one. What we are interested in is the multivariate regression equation. We want to plug in numbers and predict outcomes, right? Once again, y hat is the inferred value, and b0 is the intercept. The independent variables range from x1 to xk. b1 to bk are their corresponding coefficients. The last thing to say about multivariate regressions is that it's not about the best fitting line anymore. Actually, it stops being two-dimensional, and when we have over 3 dimensions, there is no visual way to represent the data. So, if it is not about the line, what is it about? It's about the best fitting model. As we saw from the OLS, what we really want is the least sum of squared errors. Alright, so how do we decrease the model's error? Well, by increasing the explanatory power of the model. SSE and SSR are like communicating vessels, remember? Each time we lower one, the other goes higher. With each additional variable, we increase the explanatory power by 0 or more than 0. We cannot lower it. More variables usually equal a better fitting model. In the next lesson, we will see how to determine the optimal number of variables to use. Thanks for watching.
Lecture 52, Adjusted R-squared.
Remember when we talked about R-squared and I told you it was a very widely used measure of explanatory power? Well, that was almost true. We'll have to refine this measure. Its new version will be called the adjusted R-squared. A statistician would always look at it when performing regression analysis. So what does it adjust for? Let's consider 2 statements we saw in the previous lessons. 1. The R-squared measures how much of the total variability is explained by our model. And 2. Multivariate regressions are always better than univariate, as with each additional variable you add, the explanatory power may only increase or stay the same. Well, the adjusted R-squared considers exactly that. It measures how much of the total variability is explained by our model, considering the number of variables. The adjusted R-squared is always smaller than the R-squared, as it penalizes excessive use of variables. Think about our SAT scores example. It had an R-squared of 0.406 and an adjusted R-squared of 0.399. Now, let's add another variable called random123. I've generated a variable that assigns 1, 2, or 3 randomly to each student. We are 100% sure this variable cannot predict college GPA. So, this is our new model. College GPA is equal to B0 plus B1 times SAT score plus B2 times the random variable. Let's check out the newly created regression tables. We can see the new R-squared is 0.407, so it seems we have increased the explanatory power of the model. But then, our enthusiasm is dampened by the adjusted R-squared of 0.393. We were penalized for adding an additional variable that had no strong explanatory power. We have added information but have lost value. The point is, you should cherry-pick your data to exclude useless information. However, one would assume that regression analysis is smarter than that, right? Adding an impractical variable should be pointed out by the model. Well, that's true. Look at the coefficients table. We have determined a coefficient for the random 1, 2, 3 variable, but its p-value is 0.677. Remember the null hypothesis of the test? Beta 2 equals 0. We cannot reject the null hypothesis at the 68 significance level. This is an incredibly high p-value. Let me remind you that, for a coefficient to be statistically significant, we want a p-value of less than 0.05. Our conclusion is that the variable random 1, 2, 3 not only worsens the explanatory power of the model, reflected by a lower adjusted R-squared, but is also insignificant. Therefore, it should be dropped altogether. Dropping useless variables is important. You can see the original model changed from y hat equals 0.247 plus 0.002 times x1 plus 0.012 times x2 to y hat equals 0.4803 plus 0.0015 times x1. The choice of the third variable drastically affected our other predictors. Whenever you have one variable ruining the model, you should not use this model altogether, because the bias of this variable is reflected into the coefficients of the other variables. The correct approach is to remove it from the regression and run a new one, omitting the problematic predictor. There is one more consideration concerning the removal of variables from a model. We can add 100 variables to a model, and probably the predictive power of the model will be outstanding. However, this strategy makes regression analysis futile. You are trying to use a few independent variables that approximately predict the result. The trade-off is complex, but simplicity is better rewarded than higher explanatory power. Finally, the adjusted R-squared is the basis for comparing regression models. Once again, it only makes sense to compare two models considering the same dependent variable and using the same dataset. If we compare two models that are about two dependent variables, we will make an apples to oranges comparison. If we use different datasets, it's an apples to dinosaurs problem. As you can see, adjusted R-squared is a step in the right direction, but should not be the only measure trusted. Caution is advised, whereas thorough logic and diligence are mandatory. In our next lesson, we will learn how to assess the overall significance of a model. Thanks for watching.
Lecture 53, what does the F-statistic show us and why we need to understand it?
In the lecture about regression tables, we mentioned the F-statistic, which we saw in the ANOVA table. Let's try to explain its essence and see how it's useful to us. Much like the Z-statistic that follows a normal distribution and the T-statistic that follows the student's T-distribution, the F-statistic follows an F-distribution. I'm calling it a statistic, so it is used for tests, right? You guessed correctly. The test is known as the test for overall significance of the model. The null hypothesis is, all the betas are equal to 0 simultaneously. The alternative hypothesis is, at least one beta differs from 0. What's the interpretation? If all betas are 0, then none of the independent variables matter. Therefore, our model has no merit. Let's see the ANOVA table for the SAT score, college GPA regression. The F-statistic is 55.5, and its p-value is 0.000. We say the overall model is significant. Notice how the p-value is a universal measure for all tests. There is an F-table used for the F-statistic, but we don't need it because the p-value notion is so powerful. The F-test is important for multivariate regressions, as it gives us some important insights. Let's see the ANOVA table for the model, where we added the random 1, 2, 3 variable that had nothing to do with anything. The F-statistic is 27.8, and the p-value is 0.000. You can see the F-statistic is lower. The model is still significant, but less so. The lower the F-statistic, the closer to a non-significant model. This is yet another tool that allows us to compare models. Okay, this was the test for overall significance of the model. Don't forget to look for the 3 zeros after the dot. And thanks for watching.
Lecture 54, OLS Assumptions.
So far, we introduced quite a few notions about regressions. Most statistics books start by introducing regression assumptions directly, but we preferred to talk about the intuition behind regressions first, and then introduce you to regression assumptions. Now that we have seen quite a few lessons, we are ready to introduce regression assumptions. Here, we divide them into 5 assumptions. You should know all of them and consider them before you perform regression analysis. We will have a separate lesson for each one. The first one is linearity. It is called a linear regression. As we said earlier, there are other types of regressions with more sophisticated models. The linear regression is the simplest one and assumes linearity. Each independent variable is multiplied by a coefficient and summed up to predict the value. The second one is endogeneity of regressors. Mathematically, this is expressed as the covariance of the error and the x's is 0 for any error or x. The third assumption is normality and homoscedasticity of the error term. Normality means the error term is normally distributed. The expected value of the error is 0, as we expect to have no errors on average. Homoscedasticity, in plain English, means constant variance. We will discuss it thoroughly later. The fourth assumption is no autocorrelation. Mathematically, the covariance of any two error terms is 0. That's the assumption that would usually stop you from using a linear regression in your analysis. And the last one is no multicollinearity. Multicollinearity is observed when two or more variables have a high correlation between each other. Okay, these are the main regression assumptions. They are crucial for regression analysis. As the purpose of this section was to help you understand regressions, you should not skip any lectures about assumptions. At your workplace, the biggest mistake you can make is to perform a regression that violates one of these assumptions.
Lecture 55, A1_linearity.
The first assumption we will discuss is linearity. As we explained earlier, a linear regression is the simplest non-trivial relationship. It is called linear because the equation is linear. Each independent variable is multiplied by a coefficient and summed up to predict the value of the dependent variable. How can you verify if the relationship between two variables is linear? The easiest way is to choose an independent variable x1 and plot it against the dependent y on a scatter plot. If the data points form a pattern that looks like a straight line, then a linear regression model is suitable. Let's see a case where the assumption is violated. After plotting another variable x2 against y on a scatter plot, we see there is no straight line that fits the data well. Actually, a curved line would be a very good fit. Using a linear regression would not be appropriate. All clear? Linearity seems restrictive, but there are easy fixes for it. You can run a non-linear regression or transform your relationship. There are exponential and logarithmical transformations that can help with that. The quadratic relationship we saw in this video could be easily transformed into a straight line with the appropriate methods. The takeaway is, if the relationship is non-linear, you should not use the data before transforming it appropriately. That summarized linearity. Next assumption is endogeneity of regressors. What exactly does it mean? We'll see in the next lesson. Thanks for watching.
Lecture 56, No Endogeneity.
Alright, the second assumption is the so-called no endogeneity of regressors. It refers to the prohibition of a link between the independent variables and the errors, mathematically expressed in the following way. Think about it. Here, the error, the difference between the observed values and the predicted values, is correlated with our independent values. This is a problem referred to as omitted variable bias. Omitted variable bias is introduced to the model when you forget to include a relevant variable. As each independent variable explains y, they move together and are somewhat correlated. Similarly, y is also explained by the omitted variable, so they are also correlated. Chances are, the omitted variable is also correlated with at least one independent x. However, you forgot to include it as a regressor. Everything you don't explain with your model goes into the error. So, actually, the error becomes correlated with everything else. Before you are too confused, I'll give you an example. Imagine we are trying to predict the price of an apartment building in London based on its size. This is a rigid model that will have high explanatory power. However, From our sample, it seems that the smaller the size of the houses, the higher the price. This is extremely counterintuitive. We look for remedies, and it seems the covariance of the independent variables and the error terms is not zero. We are missing something crucial. Omitted variable bias is hard to fix. Think of all the things you may have missed that led to this poor result. We have only one variable, but when your model is exhaustive with 10 variables or more, you may feel disheartened. Critical thinking time. Where did we draw the sample from? Can we get a better sample? Why is bigger real estate cheaper? Alright, let me give you more information. The sample comprises apartment buildings in central London and was large. So the problem is not with the sample. What is it about smaller size that is making it so expensive? Where are the small houses? There is rarely construction of new apartment buildings in central London. And then you realize the City of London was in the sample, the place where most buildings and skyscrapers with some of the most valuable real estate in the world. If central London was just central London, we omitted the exact location as a variable. In almost any other city, this would not be a factor, but in our particular example, the $1 million suites in the City of London turn things around. After we include a variable that measures if the property is in London City, everything falls into place. Larger properties are more expensive and vice versa. Okay, before we wrap up, an important remark. The incorrect exclusion of a variable, like in this case, leads to biased and counterintuitive estimates that are toxic to your regression analysis. An incorrect inclusion of a variable, as we saw in our adjusted R-squared lecture, leads to inefficient estimates, which don't bias the regression and you can immediately drop them. So, when in doubt, just include the variables and try your luck. What's the bottom line? Omitted variable bias is a pain in the neck. It is always different, always sneaky, and only experience and advanced knowledge on the subject can help. Always check for it, and if you can't think of anything, ask a colleague for assistance.
Lecture 57, A3 _ Normality and Homoscedasticity.
Okay, great. So far, we've seen assumptions 1 and 2. Here's the third one. It comprises of 3 parts: normality, zero mean, and homoscedasticity of the error term. The first one is easy. We assume the error term is normally distributed. Normal distribution is not required for creating the regression, but for making inferences. Remember all regression tables were full of T-statistics and F-statistics? Well, these things work because we assume normality of the error term. What should we do if the error term is not normally distributed? You probably remember the theorem we studied earlier in the course, right? Yes, that's right, the central limit theorem. For large samples, the central limit theorem applies for the error terms too. Therefore, we can consider normality as a given for us. What about a zero mean of error terms? Well, if the mean is not expected to be zero, then the line is not the best fitting one. However, having an intercept solves that problem, so in real life it is unusual to violate this part of the assumption. And homoscedasticity, what's that about? It means to have equal variance. So, the error terms should have equal variance one with the other. What if there was a pattern in the variance? Well, an example of a dataset where errors have a different variance looks like this, starting close to the regression line and going further away. This would imply that, for smaller values of the independent and dependent variables, we would have a better prediction than for the bigger values. And I assure you, we really don't like this uncertainty. Let's see a real-life example. Most examples related to income are heteroscedastic with varying variance. If a person is poor, he or she spends a constant amount of money on food, entertainment, clothes, etc. The wealthier an individual is, the higher the variability of his expenditure. For example, a poor person may be forced to eat eggs or potatoes every day. Both meals cost a similar amount of money. A wealthy person, however, may go to a fancy gourmet restaurant, where truffles are served with expensive champagne one day and stay home and boil eggs the next day. The variability of his spending habits is tremendous. Therefore, we expect heteroscedasticity. Well then, is there a way to circumvent heteroscedasticity? First, check for omitted variable bias. That's always an idea. After that, you can look for outliers and try to remove them. Finally, we shouldn't forget about a statistician's best friend, the log transformation. Naturally, log stands for a logarithm. You can change the scale of the graph to a log scale. For each observation in the dependent variable, calculate its natural log and then create a regression between the log of y and the independent x's. Conversely, you can take the independent x that is causing you trouble and do the same. Let's see an example. This is a scatter plot that represents a high level of heteroscedasticity. On the left-hand side of the chart, the variance of the error is small, while on the right, it is high. Here's the model. As x increases by 1 unit, y grows by b1 units. Let's transform the x variable to a new variable called log of x and plot the data. This is the new result. Changing the scale of x would reduce the width of the graph. You can see how the points came closer to each other from left to right. The new model is called a semi-log model. What if we transform the y-scale instead? Analogically to what happened previously, we would expect the height of the graph to be reduced. That's the result. This looks like good linear regression material, doesn't it? The heteroscedasticity we observed earlier is almost gone. This new model is also called a semi-log model. Its meaning is, as x increases by 1 unit, y changes by b1%. This is a very common transformation. Sometimes we want or need to change both scales to log. The result is a log-to-log model. We shrink the graph in height and in width. This is the result. The improvement is noticeable, but not game-changing. However, we may be sure the assumption is not violated. The interpretation is, for each percentage point change in x, y changes by b1 percentage points. If you've done economics, you would recognize that such a relationship is known as elasticity. Alright, we are done here. 3 assumptions down, 2 to go. Great work!
Lecture 58, A4_No Autocorrelation.
The penultimate assumption is the no autocorrelation assumption. It is also known as no serial correlation. This is my least favorite, as it cannot be relaxed. Mathematically, it looks like this. Errors are assumed to be uncorrelated. Where can we observe serial correlation between errors? It is highly unlikely to find it in data taken at one moment of time, known as cross-sectional data. However, it is very common in time series data. Think about stock prices. Every day you have a new quote for the same stock. These new numbers you see have the same underlying asset. Without getting too much into the finance, ideally, you want them to be random or predicted by macro factors, such as GDP, tax rate, political events, and so on. Unfortunately, it is common in underdeveloped markets to see patterns in the stock prices. There is a well-known phenomenon called the day of the week effect. It consists in disproportionately high returns on Fridays and low returns on Mondays. There is no consensus of the true nature of the day of the week effect. One possible explanation, proposed by Nobel Prize winner Merton Miller, is that investors don't have time to read all the news immediately, so they do it over the weekend. The first day to respond to the negative information is on Mondays. Then, during the week, their advisors give them new positive information, and they start buying on Thursdays and Fridays. Another famous explanation is given by the distinguished financier Kenneth French, who suggested firms delay bad news for the weekends, so markets react on Mondays. Whatever the reason, there is a correlation of the errors when building regressions about stock prices. The first observation, the 6th, the 11th, and the 5th onwards would be Mondays. The 5th, 10th, and so on would be Fridays. Errors on Mondays would be biased downwards, and errors for Fridays would be biased upwards. The mathematics of the linear regression does not consider this. It assumes errors should be randomly spread around the regression line. So, how does one detect autocorrelation? A common way is to plot all the residuals on a graph and look for patterns. If you can't find any, you're safe. But what's the remedy, you may ask? The remedy is, there is no remedy. I told you in the beginning of this lecture, you cannot relax this assumption. The only thing you can do is avoid using a linear regression in such a setting. There are other types of regressions that deal with time series data. It is possible to use an autoregressive model, a moving average model, or even an autoregressive moving average model. And I'm not done yet. There's also an autoregressive integrated moving average model. Make your choice as you will, but don't use the linear regression model when error terms are autocorrelated. Our next lesson will be a lot more encouraging, I promise. See you there.
Lecture 59, A5_No Multicollinearity.
The last assumption is no multicollinearity. We observe multicollinearity when two or more variables have high correlation. Let's exemplify this point with an equation. A is equal to 2 plus 5 times B. A and B are two variables with an exact linear combination. A can be represented using B, and B can be represented using A. In a model containing A and B, we would have perfect multicollinearity. This imposes a big problem to our regression model, as the coefficients will be wrongly estimated. The reasoning is that, if A can be represented using B, there is no point using both. We can just keep one of them. Alright, another example would be two variables C and D, with a correlation of 90%. If we had a regression model using C and D, we would also have multicollinearity, although not perfect. Here, the assumption is still violated and poses a problem to our model. Usually, real-life examples are helpful, so let's provide one. There are two bars in the neighborhood, Bonkers and the Shakespeare Bar. We want to predict the market share of Bonkers. Most people living in the neighborhood drink only beer in the bars. So, a good approximation would be a model with three variables: the price of half a pint of beer at Bonkers, the price of a pint of beer at Bonkers, and the price of a pint of beer at Shakespeare's. This is logical, right? If one bar raises prices, people would simply switch bars, so the price in one bar is a predictor of the market share of the other bar. Alright, where's the problem? Half a pint of beer at Bonkers costs around $1, and one pint costs $1.90. Bonkers tries to gain market share by cutting its price to 90 cents. It cannot keep the price of one pint at $1.90 because people would just buy 2 times half a pint for $1.80. Bonkers management lowers the price of the pint of beer to $1.70. Next, we run a regression based on these three variables. The p-value for the pint of beer at Bonkers and half a pint at Bonkers show they are insignificant. Why? The underlying logic behind our model was so rigid. Well, no multicollinearity is an assumption of the calculations behind the regression. The price of half a pint and a full pint at Bonkers definitely moved together. This messed up the calculations of the computer, and it provided us with wrong estimates and wrong p-values. So how do we fix it? There are three types of fixes. The first one is to drop one of the two variables. The second is to transform them into one variable. The third possibility is tricky. If you are super confident in your skills, you can keep them both while treating them with extreme caution. The correct approach depends on the research at hand. Multicollinearity is a big problem, but is also the easiest to notice. Before creating the regression, find the correlation between each two pairs of the independent variables, and you will know if a multicollinearity problem may arise.
Lecture 60, Dummy Variables.
Congratulations on reaching the last lesson of our regression analysis section. Our focus here will be dummy variables. Apart from the offensive side of the word, there is another meaning, an imitation or a copy that stands as a substitute. In regression analysis, a dummy is a variable that is used to include categorical data into a regression model. So far, we used only numerical data, like the SAT score and the GPA, or the random 1, 2, 3 variable from the adjusted R-squared lesson. Now we will explore how to include variables such as gender, season, and brand into a regression we are working with. For instance, let's take our GPA prediction example that we all know so very well. Generally, another good and suitable regressor for GPA is attendance. Here is a dataset that includes a variable that measures if a student attended more than 75% of their university lectures. This is categorical data, so we cannot simply put it in the regression. Our approach for this lesson will be to go through the process of using a dummy and explain it later on. Okay, here we go. Let's include another column that is called dummy attendance. That is our dummy variable. If the student attended more than 75% of the lessons, the dummy will be equal to 1, otherwise it will be a 0. So, we have transformed our yes or no question into ones and zeros. That's what the dummy name stands for. We are imitating the categories with numbers. Alright, I don't need the original attendance variable anymore as the dummy contains the same information. Let's create a regression that explains the GPA with both SAT scores and attendance. The result is the following. Our overall model is significant. The SAT score is significant and the dummy is significant, although barely so. The adjusted R-squared of this model is 0.422, which is an improvement from the 0.399 we got last time without attendance. That's not game-changing, but is still relevant. The original model without the dummy variable was GPA equals 0.48 plus 0.0015 times the SAT score of a student. The model, including the dummy variable, is GPA equals 0.87 plus 0.0013 times the SAT score of a student plus 0.1184 times the dummy. Now, we said that the dummy is 1 or 0, so we can actually represent this equation with two others. If the student did not attend, the dummy will be 0, so 0.1184 times 0 is 0. The model becomes GPA equals 0.87 plus 0.0013 times SAT. If the student attended, the dummy will be 1, so the model becomes GPA equals 0.87 plus 0.0013 times SAT plus 0.1184. Let's add the intercept and the dummy together. We get GPA equals 0.99 plus 0.0013 times SAT. Graphically, this looks in the following way. So we have two models that have the same slope, but they have a different intercept. The students who attended are spread around the upper line. On average, their GPA is 0.1184 higher than the GPA of students who did not attend. Okay, to use this model for prediction, we need two pieces of information: an SAT score and the information whether a person attended more than 75% of their lectures. For example, Joshua got 1700 on his SAT and did not attend 75% of his lessons. Our model predicts that his graduation GPA will be 3.08. Jennifer, on the other hand, got 1670 on the SAT but attended all of her lectures. According to our regression, she is expected to graduate with 3.16. As you can see, although she scored lower on the SAT, her attendance turned things around for her. Had we used our previous model without the dummy variable, we would have predicted that Joshua would graduate with 3.03 and Jenny with 2.99. While Joshua's GPA barely changed, we see a significant difference in the prediction about Jenny. Okay, this will do. In our next lesson, we will solve a practical example. We will even use several dummy variables, which will ensure you will reinforce what you've learned here. See you next time, and thanks for watching.
Lecture 61. Practical Example Regression Analysis.
Hey, if this section seems too theoretical, now is the time to prove you wrong. We will deal with a real-life example about car sales. Actually, it is so real-life that it is very messy, and we will need to first clean our dataset, then go through several assumptions, relax some on them, practice with the concept of log transformation we mentioned earlier, create a model, and we will eventually finish off with some dummy variables. I bet you will be blown away by all the things you already know. Everything will be interconnected, so get comfortable and let's start analyzing. Here's our dataset. This is a list of second-hand cars with their respective price, type of body, mileage, engine volume, engine type, year of production, and model. What we would like to do is predict the price of a used car, depending on its specifications. The first potential regressor is brand, as it is well known that a BMW is generally more expensive than a Toyota. The second relevant variable is mileage, since the more a car is driven, the cheaper it should be. Third, the engine volume. Sports cars have larger engines, and economy cars have smaller engines. And the final variable is year of production. The older the car, the cheaper it is, with the exception of vintage vehicles. These are the variables we will focus on. Alright, we haven't spoken about data cleaning so far in this course. Our focus was statistics, so I was always cleaning the datasets for you before presenting them. This time it will be different, and you will get a feeling of what raw data looks like. I will go column by column. Excel is not optimized for data analysis, but it has sufficient resources for our current needs. An easy way to spot problems with your data in Excel, such as missing values, is to sort the cells. So, I'll start sorting the relevant cells. Brand looks fine. Price, however, has lots of missing values. There are different methodologies for sorting this out, but I will simply remove all observations that do not include a price. As price is the dependent variable, it is a big issue in our analysis if there is no price listed. A rule of thumb is that if you are removing less than 5% of the observations, you are free to just remove all observations that have missing values. In this case, they are 4.4%. The next variable is mileage in thousands of miles. There are missing values for it as well. We are not sure if these are zeros or something else. Looking at the year of production and the price, they most likely are. While more diligence should be applied, I'll just add zeros here. The next variable is the engine. We can see many values that are not available. It's best to delete these variables. Okay, but then there are also the engine volume values of 99.99, 90, 75, etc. I am no car expert, but these are not usual values. Moreover, looking through all 4,000 plus values, we notice that most entries are in the range from 0.6 to 6.5. A quick search on Google would confirm that's the interval where engine volume should fall. Therefore, those 99.99s, 90s, and so on are incorrect entries. Actually, a common way to label missing values is by assigning 99.99. That's something that's stuck from the early ages of computers. It is a bad idea to label values in such ways, as it is very hard for other users of the data to distinguish them from the true values. However, be aware that some people still do it. Let's remove these entries. The last value of interest is the year when a car was produced. There are no problems with it. We are good to go. Alright. So far, we have identified brand, mileage, engine volume, and year of production as regressors. Brand is categorical data. Linearity is not going to be an issue there, as the brand will be included in the regression through dummy variables. We are left with price, mileage, and year, where price is the dependent variable of the regression. Let's check for linearity using a scatterplot. These are the three scatterplots that we obtain. One for price and mileage, one for price and year, and one for price and engine volume. We can spot patterns, but definitely not linear ones projected by Excel with the orange trend line. We know we should not run a linear regression in this case. We should first transform one or more variables. As I have told you before, log transformation is a common way of dealing with this issue. It is especially useful when facing exponential scatterplots like we do now. Let's take the log of prices and plot them again. Alright, we can see a linear pattern in the plots now. The lines fit the data so much better. However, I'd like to take the log of mileage and do a log-log scatterplot, as I suspect that we will get even better results. Okay, I was kind of wrong. It is hard to say if this is an improvement. But let's keep the log of mileage in the regression, as to see how is a log-log relationship interpreted. Superb. Next, we have to deal with the no endogeneity assumption. There are tests to check if it is violated, or one can take the residuals and find their correlation with each independent x. I can tell you that the assumption is not violated, so it is of no interest. The third assumption had several parts. Normality is assumed for a big sample, following the central limit theorem. The zero mean of the distribution of errors is accomplished through the inclusions of the intercept in the regression. Finally, the homoscedasticity assumption generally holds, as we can see in the graphs. The reason for that is that we already implemented a log transformation, which is the most common fix for heteroscedasticity. The fourth assumption is no autocorrelation. We don't really need to put much effort into that. The observations we have are not coming from time series data or panel data. They are simply a snapshot of the current situation at a secondhand car sales website. Each row comes from a different customer who is willing to sell their car through the platform. Logically, there is no reason for the observations to be dependent on each other. We're safe. Finally, we should check for multicollinearity. That can be done by finding the correlations of all possible pairs of variables. Mileage with year, mileage with engine volume, and year with engine volume. The correlations are far from strong, so we can conclude that we are not in the presence of multicollinearity. After having checked the assumptions, we can finally create the regression. First, let's explain log price with log mileage. Okay. We can see that the model is significant. The explanatory variable is significant too, and the r² of the regression is 0.27. So, we have some explanatory power, but this is not a very powerful model. Similarly, the r² of a regression of price with engine volume is 0.21. Next, let's explain log price with year. Both the model and the variable are significant. The r² is 0.56, so year explains 56% of the variability of a car's price. That's a remarkable relationship. Now, let's create a regression using all three variables: mileage, year, and engine volume. The model and all variables are significant. We already expected that, given that we created 3 regressions earlier. However, this time, the adjusted r² is 0.77. Therefore, the 3 variables together explain 77% of the total variability. That's a very nice and rigid model already. To conclude the example, we would like to include the brand in the regression. There are 7 brands: Audi, BMW, Mercedes, Mitsubishi, Renault, Toyota, and Volkswagen. This is categorical data. In order to include it in the regression, we have to create dummy variables. Audi dummy would be 1 if the brand is Audi, and 0 if it is not. BMW dummy would be 1 if the brand is BMW, and 0 if it is not, and so on. For the last brand, in this case Volkswagen, we will not create a dummy variable. The reasoning is the following. If all other dummy variables are 0, it is clear that the car is Volkswagen. If we include a separate variable called Volkswagen, we will introduce multicollinearity to the regression. The Volkswagen dummy would be perfectly determined by the other variables. Thus, if we have n categories, there will be only n-1 dummies. We are basically creating the dummy variables as we did in our previous lesson. Now, let's run a new regression, including the dummies. The final model that we get is significant. Moreover, each variable included is significant. The adjusted R-squared of the model is 0.8. This regression has a very high explanatory power. The only thing we have left is to interpret the result. The model is the log of price equals minus 78.41 plus minus 0.11 times log of mileage plus 0.14 times the engine volume plus 0.04 times the year of the car plus the dummies. Let's look at them one by one. Keep in mind that our dependent variable is the logarithm of the price, so the interpretation will be a bit different than usual. The intercept is clear. Mileage. The log of price changes by minus 0.11 times log of mileage. As I told you in one of our previous lessons, this can be interpreted in the following way. For each percentage change in mileage, the price decreases by 0.11%. Engine volume. The interpretation is the following. For each extra unit, or liter, of engine volume, the logarithm of price increases by 0.14. To see the impact on price, we have to get back to the original variable. The same way multiplying and dividing are opposite operations, taking the exponential and taking the log are too. There are further explanations in the course notes, but bear with me. Log price changes by 0.14. Normal price is equal to e to the power of log price. So, to get the change in price, we should find the exponential of 0.14. Therefore, the price would change to 1.15 of its original value. That is a 1.15 minus 1% increase, or 15%. Once again, please check the course notes if you need clarification of the math involved. Year of production. For each additional year, the price increases by the exponential of 0.04 minus 1 in percentages. That is 4%. Finally, we have the dummies. We have 6 dummies: Audi, BMW, Mercedes, Mitsubishi, Renault, and Toyota. We haven't included Volkswagen as we said that the dummy should be one less than the options. So, if all dummies are null, then we get this model. Another fact is that if all dummies are null, then the car is not Audi, BMW, Mercedes, Mitsubishi, Renault, or Toyota. It is a Volkswagen. So actually, the dummies give us a comparison with the Volkswagen car. That's the benchmark. The coefficient of the Audi dummy is 0.06. Therefore, all else being equal, the price of an Audi is 6% higher than a Volkswagen's price. Similarly, the prices of a BMW and Mercedes are 12% and 11% more than that of a Volkswagen. A Mitsubishi is 5% cheaper, and a Renault is the cheapest at a 17% lower price. To exhaust the dummies, all else equal, a Toyota is 4% more expensive than a Volkswagen. Alright, this wraps up our exercise on regression analysis. This was my favorite topic so far, and I hope you had fun. See you next time, and thanks for watching.